Hello everyone. Today we'll continue building our JavaScript interpreter. In the last lesson we were able to take a string of source code and transform it into a list of tokens, and the next step is to transform this list of tokens into an abstract syntax tree, the thing you're seeing right here. Now, why do we need this abstract syntax tree? Well, take a look at this expression right here. If we want to calculate this in our head, we have certain precedence rules in mind. So we know that parentheses come first because of the PEMDAS rule. So 6 minus 3 will be computed first in our head. After that follows the 2 times 6 minus 3. Then we have this minus 3, and we add that to this expression, right? Now, for us this is intuitive, right? We just have these rules in mind and we can apply them directly. For a computer, it isn't that intuitive. We have to somehow transform this list of tokens to a more intuitive thing for a computer. And here's where abstract syntax trees come into play. So we create this tree-like structure where the things deeper in the tree have to be computed first. So if we're trying to compute this, for example, we first have to be able to be computing this. And to compute this, we first have to know what this results in. And to understand what this group results in, we have to look at this binary operator. And you can see right here that you first have to compute the stuff deeper in the tree and move up your way and compute your way up, so to say, such that you can get this final expression, so the result of our expression right here. And well, let me give you an understanding of what these words mean. Bin stands for a binary operation, so an operation like addition or multiplication or subtraction or division, because these operations take two numbers and an operator, right? So these are binary operations. And then we have groups for things grouped inside of parentheses. We have lit for literals, so values like 2 and 3. And for now we'll only be building an arithmetic parser, but we'll level that up to be able to also parse Boolean expressions and comparisons and all that sort of stuff. So to parse any expression really in JavaScript, and then we'll also get to statements, but that's for future episodes. For now we'll only be focusing on arithmetic stuff. And yeah, lit is for literals, so numbers, but we'll get to Boolean literals or string literals. And then we also have unary things, so unary operations that take some kind of expression and perform some operator on it. So, for example, the unary minus operator takes a number and makes it negative or positive, depending if it was negative before. So you see how this works. This also works with the exclamation mark or bang operator, we call it. For example, if you bang true, then it becomes false. So you get the idea. And yeah, in this episode we'll be able to transform this into this abstract syntax tree. So yeah, but before jumping into the implementation of this parser, we first have to fix some bugs that I introduced in the last lesson. So firstly, I forgot to consume the closing parentheses after handling the string. So let's consume that, and for example say that there should be no case where the string doesn't terminate with this operator in here, so that shouldn't be a problem, but we can just still use that unterminated string. How does the consume method look like? Or do we have a consume method? No, we don't. Do we? No. Well, we can just advance over that. Or how do we advance? Well, I forgot all of this. Yeah, we just increment current, I guess. Okay. Like that. So that we skip over this closing quotation mark. And here I forgot to ensure that digits are also handled, because variable names can also be digits, right? So let's do this. Is digit and put in current, like so. Okay, nice. And now we can actually get to the parser. So we were able to create this linear list of tokens. So now let's create a new folder for the parsers, or a new directory, and let's create the parser header file and the source file. So well, all this file will really do is it'll take in this linear list of tokens to work with it. So let's do that. Tokens, like so, and let's import the tokens. And now what we'll do is we'll also store these tokens as a field. And now let's define this constructor to just initialize this end tokens with the pass in tokens. We won't do more in there. Okay, and now we'll actually have to add this parse method. And this parse method should return an expression, right? So we'll have to define some sort of expression class, and let's do that in here. A new directory for their expressions, and let's create an expression header. So as I've mentioned, these expressions can be like of 4 different types. We'll sort of add to this expression, to these expression types when the language gets more complex, but for now we'll only keep it simple and only have 4. So this will be a variant, and this variant type is very nice because it's from the C++ standard. It's part of the SCL, and it's super nice for interpreter and parser programming, because you can use something called visit, which we'll get to. But let's first just define this. Basically, you can pass in as many types in here as you like, and this is just a type-safe union. So let's call that value, and this variant, well, it, as we've mentioned, there can be unary inside of it, a binary, a group, and a literal. So let's just define all of these. Like so. And now in here we'll just use the unary, binary, group, and literal, like so. Perfect. And now let's actually try to fill these, well, we'll try to fill these different kinds of expressions. So the unary, well, it just has a token for the operator, for the unary operator, because for example there could be the minus operator or the bang operator, right? So that's that. And next to this unary operator you also need the expression to which this operator is being applied to, and here we come to a problem. You might ask yourself why. Well, we have a circular import. Expression depends on unary, since it needs it to be defined inside of the variant, and the unary imports the expression. So this is like a circular import, and that doesn't work. The way we solve this is pretty simple. We'll just create an expression forward declaration header file, and in there, well, what we'll do is we'll forward declare expression, like so, and we'll not import expression. And another thing we'll do is we'll create an expression pointer alias using set unique pointer and passing an expression in here. For that we have to include memory. And now we have that. Now what we do is, instead of importing expression, we just import expression forward. And instead of using expression here, we will be using expression pointer. And then this will just be initially a null pointer. And this works perfectly because, well, now unary doesn't depend on expression, and expression can still import unary. Now let's do the same for binary. So it'll look very similar, but instead of unary operator, we'll have a binary operator, and we'll also have a right expression, but next to that we'll also have a left expression. Now in the group, we'll just have an expression for the value that's being grouped, and this, this group thing, you might argue that this is overkill and not needed, because you could just as well program it without this, but I'll just keep it because it makes things more clear, I feel like. And now this literal, that's more interesting, because in here we have to store like some kind of value, right? A number or a string or a boolean. So for that we'll create a new a file called the JavaScript value file, and in there we'll define like the skeleton of a JavaScript value in our in our language. And a JavaScript value we can just call that value. It doesn't have to be called JavaScript value because it's already in the JavaScript++ namespace. Well, a value is once again a variant, because a value can be multiple things. It could be a double, it could be a bool, it could be a string, right? So use all of that, and we'll put a bool in there, a double, and we don't have to differentiate between integers and integers and floating point numbers, because in JavaScript everything's just of type number. So for example, this right here would be true, and we'll also have a string, and we'll also add to that. Well, if we get, for example, the object-oriented programming, value must also support objects, but that's once again a topic for another lesson. Okay, now that we have that JavaScript value, we'll put that in here, value. That's our value. Okay, perfect. Nice. Now we've got to a point where we've got all the basic setup done, and we can now start actually parsing. So we'll return an expression pointer and call this parse. And what this method does is it parses these tokens. So once again, we have to like traverse through our input, so we'll need some kind of current that tells us where we are in this tokens list. And this is very similar to the Lexer, because we'll also need these methods like isAtEnd, or we'll also need methods like advance that advances the token or the current and returns you the current token. Or what else do we need? Well, we also need to be able to get the current or the previous one. We need to be able to consume the token, and also throw an error message if it failed to consume it. So let's call it error message. Yeah, but well, we'll add to this once we need more. So let's go to the source. Let's first define all of these. This is for the parser, and let's do that 3 more times, like so. So what we'll do in here is, wait, do we have the isAtEnd? No. Oh no. Okay. Well, the isAtEnd, what this does is it checks if the current is, if m tokens at the index of m current is at the end of the file. So if that type is at the end of the file, So I have to put in type in here, and we'll return that. And that can be const qualified. Let's put const everywhere where it can be const qualified, like so. And in here and in here. What we have to do in here is pretty straightforward. We have to return tokens at current, like so. And for the previous, we do the same, but -1. For the advanced, well, all we do is, if we're at the end, well, then we'll return, if you're not at the end, we'll increment current, like so, and then we'll just return tokens at current. And what consume does is basically it checks if the current one is of the same type as t. If it isn't, then it will throw a std runtime error with that error message. And let's make that a string view and put in data in here and change the signature. Okay, perfect. So now we got all of these helper methods, which will help us a lot. And now we can start defining this parse method, which returns an expression pointer. So what we do is, well, now this is the tricky part, right? How do we build a tree that already encaptures a precedence? And the answer for that is very interesting. So what we basically do is we ensure that there's precedence encoded in our tree by basically giving different kind of, like, creating a hierarchy. So obviously the parentheses stuff is, or let's try to understand what has the highest value. We know from PEMDAS that parentheses have the highest value, but next to that also numbers have the highest, like, precedence, because, like, with numbers they're already done, like, you don't have to compute further stuff. So numbers have the highest value and parentheses. So let's just why did I write 2R? Okay, numbers and parentheses. After numbers and parentheses, we have these unary operators. For example, if we calculate -3 times 2, we don't calculate 3 times 2 first. We are like, okay, this is -3, and then we calculate this. So after this comes the unary operators. After unaries, we have the multiplication and division, so factors. And after factors, we have terms, so the addition and stuff like that. And basically, how we ensure that this tree is aware of these precedence rules is we won't start processing terms until factors are done being processed. And we won't start, like, the building blocks for building factors. Factors produce binaries, right? And a binary with an operator and a left and a right. And the left and the right can't be built from stuff lower down the hierarchy, but only from the unaries. And the unaries, they can be built with factors or terms, but only with numbers and parentheses. And this technique is called recursive descent parsing, and it's very powerful. Okay, so what we'll do is we'll have this term, the factor, the unary, and the literal. And as we've just said, the one with the lowest precedence is terms for arithmetic operations right now. So we'll just, when we're passing, we'll just return that. And after doing that, let's define the terms. And the building block for the terms are these factors. So we won't start parsing the terms until the factors are done. So we'll call factor in here, like so. Okay, and then we'll also return them. And these factors, they handle their stuff, right? But once they are finished, then we know it's the turn of the terms. So then we can start handling plus addition or subtraction. So if we match plus or minus, then we can kind of handle that. So let's define a match method, which returns a bool and takes in a token. Yeah, and in here, what we'll do is if the current dot type equals t, then we know that we matched, and we can increment current and return true because we had a match. Otherwise, we'll return false. So this just matches the current. It's the current, the one we provided in there. So we've parsed the factor. Is there a match of a token type of plus or a token type of minus? Like so. If there is, well, then let's get that operator, because we'll be creating this binary thing. So let's just call it op with previous. And now let's get the term to the right, because we're trying to build a binary, right? So binary operation, because plus and minus is a binary operation. So the right guy is once again a factor. Well, yeah, that's the building block for the terms once again. And then left, the thing we'll be returning is a we make another expression. We make another expression pointer, and in there because the expression just consists of this value, we have to create one of these guys. So we create a binary, since it's a binary operation, and we need to include that. And then we have to fill this binary with well, let's remove the left guy right here. Then we have the operator, and then we move the right, like so. This fails right now because we are only using the forward declaration, so it needs context of the entire thing to actually be able to create that. Okay, and that's already it. Now we can go on to the factors. And the factor basically works the exact same way, but it's one higher up in the hierarchy, so it doesn't refer to the term, but it's like next highest precedence thing is the unary, right? So we'll it has to refer to the unary instead of the factor, and also it doesn't match this plus or minus, but star and slash, like so. Okay. Now the unary, you might think that would look the exact same, but just with literal, and you could assume that, and that also is intuitive. However, the unaries are a bit different because they're right associative. So for example, if you have 3 plus 2 plus 4, what you do is you first calculate this and then this, because it's right associative. So for example, if you have 3 minus 2 minus 1, if you were to calculate 2 minus 1 first and then 3 minus 1, then you'd get 2. If you first calculate 3 minus 2 and then minus 1, you get 0. So you see that this associativity is important. With unary, it's similar. However, instead of it being left associative, so the left guy gets calculated first, it's right associative, meaning that if you have some, for example, negative, negative, negative 3, it first does this, then it does this, and then it does this. And you see the right person is first being evaluated, and that's why we call it right associative. So we can't just do this, because this already takes the left first, but the operator comes first, right? So what we have to do is we have to say, okay, if we don't match the token type of minus. Another unary operator is bang, but we won't, the exclamation mark, but we won't handle it right now because, well, I want to keep it simple for this episode because otherwise it would exceed time-wise. Well, if we don't match a minus, so a unary operator, then we know that there must come a literal. So we'll just call that, and that's the highest hierarchy thing, right? So we'll just return this literal. Otherwise, we know that we have this minus operator. So we'll, in the previous guy, there's the minus. So we'll get the operator, so this is the unary operator. And then, once again, we'll take the right guy, and that is a unary. And what we do in there is we now, we have the right, and that's the unary. I think we can now already create the expression, but it's not a binary inside, but a unary. And what we do in there is, how does the unary look like? Well, first comes the operator, and then we move the right. And I believe that should be it. Yeah, that looks fine to me. Okay. Now, the last thing that we have is the literal, and these are the easiest ones, because all we have to do is, we just have to handle them. So, if we match the token type, which token type? The number, for example, all we do is we return once again, we make a unique a unique expression, but instead of literal unary, we use literal in here, and what we put in here is std string to double of the previous token, because we matched it and consumed it right here, of the previous token lexeme. And as I've mentioned, the lexeme is the string. So if we match a number, and other token types are, for example, strings. So if we match a string, well, then we can, we don't need to put the previous, or we don't need to cast it to a double, just do this. And this already, both of these overloads work because the value is just an alias for this, and it knows how to handle that. So yeah. Now, if the match is a true or false keyword, false, then we just create a Boolean expression checking if the type is true. And if it is, then this also will be true, but otherwise it will be false. And if we get here, then we have some kind of unexpected token. So let's just throw a runtime error saying something like unexpected token. Yeah. And this seems to already be it, if I'm not mistaken. So let's try it out. Let's create a parser right here. This is our parser, and we inject our tokens in there. And after doing that, we'll call parser.parse. And if everything went right, then, okay, we have an error. I believe I know what the error is. Yeah, once again, we just use the forward. It needs context of the entire thing to be able to put it at, or use it as a field. So now we have an unexpected token, as you can see. And why is that? This should increment after being consumed, right? Because that's the whole point of consuming. You consume it and then you move forward. And this advanced guy, well, we increment and then we return this. This is wrong because we are skipping over one character, right? Or token. So we should return the previous one. Because imagine we're doing this for the first time. Then index would be 1 immediately and the first token would be completely ignored. So that's wrong. Yeah, we don't even handle groups. We don't handle groupings. So we gotta ensure that we handle that. So if the token type is a left parentheses, then we create a group, you know? So the way we do that is actually very nice, because this is like that. Here you can see that this literal basically moves back to this parse. So it's like a circle. Because right here you consumed the left parentheses, now you're parsing again from the beginning, because everything inside of the parentheses, whatever it is, if it's minus, plus, a multiplication, a union operator, it has the highest precedence now. So you can parse again, which gives you that expression, and now you can make another expression which is a group, and this group takes in this expression. Okay, so let's include that group. I believe this group is some kind of reserved thing, so let's call it grouping. So let's rename anywhere where we used it. So okay, nice. Now there's still this kind of error, because you need to use grouping. No matching for initialization. Is it? Did I declare it as a class? Yeah, I did. It has to be a struct because then its fields are in public. Okay. Okay, but this still isn't done because like we still have to consume the right parentheses. So let's put these expressions around that and move these expressions into there. But before doing so, we'll consume the right parentheses, and we'll say something like expected closing parentheses, like that. Perfect. Now if we build, that should be working now. Yeah, and it is. Parser should return the proper abstract syntax tree, and to check that, we'll be creating an expression printer. And this guy is responsible for printing our expressions in a pretty way. So what we'll do is we'll have these operator overloads and use them for the std_visit function. And this function, what it does is it takes in the expression variant, and it matches it to the different overloads it has defined and prints it based on that. So we'll have one for the grouping, like so, and we'll do the same for the binary and for the unary and for the literal. So what we'll do is for the grouping we'll have to have some kind of tracking of the current level that we're at. That's like the indentation we'll use, and then when we're printing, we'll print out all of these well, all of these levels as tabs. So we'll do for size t I is less than m level, I plus plus, and then we'll just see out a tab character, like so. And before doing that, let's see out a new line. And let's, here we'll be saying our type, so grouping, and then we'll increment level and decrement level, and in between that we'll visit our grouping dot value, dot dereference on this visitor. And let's do the same for the binary, but this will look a bit different. For the unary and for the literal as well. Okay, so no matching function call for set visit. We need to do that on the value, right? On the value, the expression, yeah. For that we also need like the expression header, and then we'll just say value, like so. Okay, for the binary, we'll just say binary, and then we'll still visit the left and the right. So we'll say binary, and we'll put in our operator in there. So the operator that's being used, like so, grouping dot binary operator dot lexeme, and let's not call that binary grouping dot binary. And then we'll say binary left first, the left value, and then the right value. Nice. Okay, now let's do that for the unary, and let's maybe copy that. Unary, grouping, unary operator, we'll call that unary. And then what we're doing here is we'll say unary dot right dot value, like so. And the lexeme, all this guy does is it just prints lexeme, like so. Okay, now we have a pretty printer, and what we do now is we can just call std visit on this expression. So let's do value, let's get that for the expression printer, creating an instance of that expression printer, like so. And if we've done everything right, the expression being created should look proper. So we have a binary of multiplication first, and that's this one. And if we take a look at the deepest level right here, that's this for the division. And if we take a look at this is the second level. And you see right here, you have the grouping first. So the lexeme, this guy, is 5, most likely. And then you have this grouping, right? And this grouping is just, this group. And then in there you have the binary for the plus, which has the lexeme on the left side of 2, and 3 divided by 2 on the right side. And this is 3 and this is 2. Yeah, so you can see right here that we've basically been able to like create an entire abstract syntax tree just from our tokens. And this is a huge step for our parser. So yeah, in next episodes we'll basically refine this expression parser to like handle more complex stuff. For example, Boolean stuff, equality and stuff like that. And then we'll get to statements. So yeah, this will be very cool in a few episodes. Okay, yeah. So that's basically it. If you learned something, make sure to leave a like and subscribe to the channel. Okay, bye bye.